Okay, this is my second video now for integrating rational functions. On the last one, I gave you an example where the degree at the top was not smaller than the degree at the bottom when we used long division first. Now I want to get to the case where the degree at the top is less than the degree at the bottom, and for an example, I chose this particular integral. The degree at the top is 1, the degree at the bottom is 2. So this does fit the pattern, which needs to be there to use partial fraction decomposition. Now this is really a lot like the opposite of adding two fractions using a common denominator. We're going to kind of unadd the two fractions now. So just to point this out, if I had a fraction like 5 over 12, okay, this could have been obtained from adding two fractions, one with denominator 4 and another with denominator 3, because the least common multiple of 4 and 3 is 12. So if I started with two fractions, something over 4 plus something over 3, and added them together, I would get something over 12. We want to do the reverse. We're starting with a fraction with 12 in the bottom, and we're trying to rewrite it as a sum of two fractions, 1 over 4 and 1 over 3. Well, this can be a tricky little problem. You might be able to guess at the answers here. Let's see here. 1/4 is 3/12, 1/3 is 4/12. So I just have to figure out what to put here and here to make these add up to 5/12. So let's see, 8/12 minus 3/12 is 5/12. So this would be 8/12. That would be 3/12. So it looks like negative and plus here. That does the trick. Okay? So we want to try to figure out how to do the same thing for this, for when we actually have polynomials instead of numbers. Well, we need to know how to factor the denominator. So what we're going to have to do with our rational function, to follow the pattern here, is to factor the denominator completely. So I chose an example where I hope we don't have much difficulty seeing the factors of the denominator. They are x plus 2 and x plus 1. So I would like to split this up as a sum of two fractions, where the denominator of one of them is x plus 2, and the denominator of the other one is x plus 1. Now the question is, what should go in the numerator? Well, we're only going to use this procedure when the degree of the numerator is smaller than the degree of the denominator. So since we started with a rational function that had that property, we expect that both of these have that property as well. Now, since the denominator is degree 1, and we want the numerator to have lower degree, there's only one choice, and that's to make it degree 0. In other words, a constant, a specific number. So I'm going to put, since I don't know what that number is, I'm going to put a letter and try to use some algebra to figure out what that letter has to represent. What number should that letter represent? And then the same thing over here. I'll call it B. So the question is, what are A and B? Okay, so we're going to use some algebra to solve this. Maybe turn it into a system of two equations and two unknowns. That ought to work. But we do have a general procedure that we can follow to help us get this. So step 1 is going to be to clear out all of our fractions. I'm going to multiply both sides of this equation by x plus 2 times x plus 1 to get rid of the fractions. Now when I do it on the left-hand side here, I end up with 2x plus 5, a fraction. Now both of these terms over here will also be multiplied by x plus 2 times x plus 1. So I get this plus b over x plus 1 times the same thing. And we can see cancellation. So my simplified equation without the fractions just looks like 2x plus 5 equals a times x plus 1 plus b times x plus 2. With a little practice, you can usually go straight from here to here without doing an intermediate step. So now the question becomes, what's a and b? Well, I have two different methods for getting my a and b. The thing to note here is that if I had two specific equations in a and b, where a and b are the unknowns, I can solve for them. And this only looks like one equation, but actually it's as many equations as you want. If you pick a specific number for x and plug it in here, you're going to get a valid equation. So this equation is true for any possible value for x. I'm going to try to pick two very nice choices to give me two nice equations, which will help me solve for a and b. Now, since this is true for any x, it's also true for x equal -1, which would make this term go away, and for x equal -2, which would make this one go away. So I'm going to use, those are going to be the two choices I use. Generally, I'm going to pick what are called the zeros of these polynomials that I get over here. So if x is -1, how does my equation read? Well, let's plug in -1 everywhere for x. This will become -2 plus 5, that's 3. This will be 0 times a, that's nothing. That's why we chose the -1 in the first place. Plus b times -1 plus 2. -1 plus 2 is 1. And this equation just turns into b equals 3. Okay, now we have the value of b. That was very convenient. Similarly, by letting x equal -2, I should be able to get the value of a. So if I plug -2 into the left-hand side, I get 1. Here, I'm going to get a times -1. And over here, I'm going to get 0. So this turns into -a equals 1, which is a equals -1. And now I have successfully performed the partial fraction decomposition. So now going back to the original question that we were trying to solve, this integral becomes the integral of a over x plus 2, where a was -1, so that's a -1 over x plus 2, and then plus b over x plus 1, where b was 3. So 3 over x plus 1. And now, technically this is a substitution, but we don't need to actually perform it. This will be minus the natural log of the absolute value of x plus 2. Plus 3 times natural log absolute value x plus 1. And there's our plus c. Now, for those of you who want a little practice, using your properties of the logarithm, one can rewrite this as the natural log of x plus 1 cubed over x plus 2